So, what is a solution for a PDE? Well, a solution is a function, and you can think of it right now as a formula, that satisfies the PDE when you substitute it in. So when you take the appropriate derivatives of it and so on and so forth, stick it into the equation, see that it matches up and turns out to be true. And you can check that a given formula is a solution by substituting it into the PDE. So that's usually the part that's fairly straightforward. So let's see. Suppose we look at the example of the heat equation. So UT is, and let's say 2 times the second derivative with respect to x. So we can check that U1 given by x squared plus 4t is a solution to this thing. If we take the first time derivative of U1, it's just going to be 4. And if we take the second space derivative of U1, then we're going to differentiate once to get 2x and then differentiate that again to get 2. And so then you can see now that if we have twice the second space derivative, that's equal to the first time derivative. And that's exactly what this equation says. Twice the second space derivative is equal to the first time derivative. But there are other solutions to this equation. So let's take like e to the minus 18t times sine of 3x. So in this case, if we look at the first time derivative of u2 here, what happens? Well, we just pull down the 18, so we get minus 18e to the negative 18t sine 3x. And if we look at the second space derivative of u2, when we differentiate the space, with respect to x twice, each time there's going to be a factor of 3 popping out of the argument here. So we'll end up with 9 total, e to the minus 18t. And then when you differentiate sine twice, you get minus sine back again. So we have this one. And you can see now that if we take 2 times the second space derivative, we get the first time derivative. So this one also satisfies the differential equation. So in general, finding the solution in the first place is where the challenge is. However, it's not always that case that it's too difficult. So let's look at a couple baby examples. So let's see. So example 1 of an equation simple enough to solve. Well, suppose that u is a function of x and t, and we want to solve ut equals 0. Well, okay. If we integrate this thing then, so let's say, so we'll take ut and we will integrate it from 0 to t. Then let's see, by fundamental theorem of calculus, this is going to be utx minus u0x. And integrating on the other side of the equation, we'll be integrating from 0 to t the function 0. And so that's going to give us 0. Now from the left side to the right side, we have that u looks like u0x. In other words, it's a constant, which is exactly what you would expect, right? So we have that the time derivative is equal to 0, then you would expect to have a constant. But look at the constant. This constant depends on x. So it's not actually a constant per se, but it's some function that depends on x, but not on time, t. All right. Let's look at another example. Let's suppose we're looking for a function of x and t that satisfies having second derivative equal to 0. So this one's not too much more difficult. We just saw in the last step that integrating once is going to give us some arbitrary function of x. So integrating again, we get that u is going to look like some arbitrary function of x times t plus some other arbitrary function of x. Okay. And what about a third example? And no, I'm not going to do the third time derivative of t. Let's do something slightly more interesting. So how about second time derivative with respect to t plus the original function gives you 0. This is just like an ODE in t because there's no time derivatives. So we know how to solve that differential equation. So we solve that ODE. And we get that u can be any cosine of t or sine of t, and then we can give either of those a coefficient, but now the coefficients are allowed to depend on x. And of course these can be added together. So that's the general form of the solution for this differential equation. And if that went a little fast for you, then check it by substituting this formula back into the given differential equation.